Welcome! In this session, we will tackle problem number 576, out of boundary paths. This is an intriguing algorithmic challenge that will test your skills in dynamic programming and recursion. Let's dive in and explore the approaches to solve this problem. In this problem, you are given an MXN grid, where a ball is placed at a specific starting position, defined by start row and start column. The ball can move in one of four directions: up, down, left, or right. However, the ball is restricted by the boundaries of the grid, meaning it cannot move beyond its edges. Your goal is to calculate the total number of ways the ball can move out of the grid boundary within a given maximum number of moves, denoted by max move. Since the result may be a very large number, you are required to return the answer modulo 10 to the power of 9 plus 7. Now, let's look at the input and output format. You will be provided with integers m and n, which represent the number of rows and columns in the grid, respectively. The maximum number of moves allowed is specified by max move, and the initial position of the ball is given by start row and start column. The output is a single integer, which represents the total number of paths that allow the ball to exit the grid boundaries within the given constraints. To better understand this problem, let's examine some examples. In the first example, the grid is defined as m equals 2 and n equals 2, meaning it is a 2 by 2 grid. The maximum number of allowed moves is max move equals 2, and the ball starts at the top left corner of the grid, specified by start row equals 0 and start column equals 0. The grid looks like this, a 2 by 2 grid with all cells initially marked as 0. The goal is to determine how many valid paths allow the ball to exit the grid boundaries within 2 moves. Now, let's analyze the first example further. Starting at 0, 0, the ball can move in several directions. For instance, moving up or left immediately takes the ball out of the grid boundary, resulting in 2 valid paths. Additionally, the ball can move right to 0, 1, and then either up or down, or it can move down to 1, 0, and then either left or right, resulting in 4 more valid paths. In total, there are 6 paths that allow the ball to exit the grid boundary within 2 moves. The final output for this example is therefore 6. Let's consider another example. Here, the grid is a single row with 3 columns, defined as m equals 1 and n equals 3. The maximum number of moves allowed is max move equals 3, and the ball starts at 0, 1, which is the middle cell of the row. The grid looks like this, a 1 by 3 grid with all cells initially marked as 0. In this case, the ball can move up, down, left, or right, and repeated combinations of these moves can eventually lead the ball out of the grid boundary. For example, the ball can move left or right to exit directly, or it can move left, then right, and then left again to exit. After considering all possible combinations, there are a total of 12 valid paths that allow the ball to exit the boundary within 3 moves. Finally, the problem also outlines constraints and edge cases, such as grids with only one cell where any move immediately leads out of bounds, or scenarios where no moves are allowed, resulting in 0 paths. These conditions help you handle different scenarios effectively. To solve the out-of-boundary paths problem, the most straightforward approach we can consider is a brute force recursive depth-first search, or DFS. Here, the intuition is simple. Starting from the initial position, the ball can move in one of 4 directions at each step, and we explore all possible paths recursively. If the ball moves out of the grid at any point during its journey, it counts as a valid path and contributes 1 to the result. On the other hand, if the ball remains inside the grid but runs out of moves, it contributes 0. The recursion depth is limited by the maximum number of moves allowed, and because the ball can start from any of the grid cells, we must account for all m*n starting positions. However, this approach comes with significant trade-offs. The time complexity is exponential, O, for max move, since there are 4 possible moves at each step, and the space complexity is O, max move, due to the recursion stack. While simple conceptually, this method is highly inefficient because it involves a lot of redundant computations. A more efficient solution is to use dynamic programming, or DP, to eliminate redundant calculations by storing intermediate results. Here, we define dp, k, I, j, as the number of ways to move out of bounds starting from cell, I, j, with exactly k moves remaining. The solution is built bottom-up, beginning with the base cases. First, if the current position I, j, is already out of bounds, then dp, k, I, j, is immediately 1, as it represents a successful path. If no moves are left, meaning k equals 0, the ball cannot leave the grid, so dp k I j is 0. The key transition relation is that dp k I j is the sum of the values from the 4 possible moves in the previous state, moving up, down, left, or right. This gives us dp k I j equals dp k1 I1 j plus dp k1 I plus 1 j plus dp k1 I j1 plus dp k1 I j plus 1. To implement this, we create a 3D dp table with dimensions, max move plus 1 ethm, and iterate through all possible move counts, rows, and columns, and compute the result for each state. Ultimately, we return the value at dp, max move, start row, start column. This approach improves efficiency significantly, with a time complexity of O, max move *m*n, and the same space complexity. To further optimize the solution, we can reduce the space complexity by observing that the current state dp, k, depends only on the previous state dp, k1. Using this insight, we can replace the full 3D dp table with just two 2D arrays, one for the previous state, previous, and one for the current state, cur. At each step, we compute the values for cur using the values from previous, based on the same transition relation as before. After processing all cells for the current move count, we simply swap the roles of previous and cur to prepare for the next iteration. This optimization reduces the space complexity from O, max move *m*n, to O, m*n, while maintaining the same time complexity of O, max move *m*n. This makes the solution much more memory efficient, particularly for larger grids or higher limits on the number of moves. The space-optimized dynamic programming approach is the best choice among the methods considered due to its balance of efficiency and simplicity. The brute force DFS approach, while easy to understand, becomes impractical for larger inputs because of its exponential time complexity. The full DP table approach solves the problem efficiently but uses unnecessary memory. By contrast, the space-optimized DP approach retains the same polynomial time complexity while significantly reducing memory usage. This makes it ideal for competitive programming scenarios or when working with constraints involving large grids or high move counts. The chosen approach works effectively because it eliminates redundant computations through DP, reducing exponential recursion to polynomial time. Additionally, the space optimization ensures the solution scales well with both grid size and move count. The underlying transition relation is intuitive and straightforward to implement, making the solution not only efficient but also robust and maintainable. Overall, the space-optimized DP strikes the perfect balance between computational efficiency and memory usage, making it the most practical solution for the problem. To solve this problem, we begin by understanding its core requirements. The input consists of a grid where a ball can roll in one of 4 possible directions: up, down, left, or right. The task is to determine whether the ball can reach a specific target position, given an initial starting position. Along with this, we must consider constraints such as boundaries of the grid and possible obstacles that may block specific paths. Next, we set up a recursive depth-first search, or DFS function, which will help us explore all possible paths. This function, called DFS row call, is designed to simulate the movement of the ball from its current position to every valid direction. Each recursive call will explore a potential path, moving step by step in one direction before trying others. To ensure the algorithm stops appropriately, we define base cases. If the ball moves out of the grid's bounds or encounters an obstacle, the recursive call is terminated. If the ball's current position matches the target, we return true, marking success. Additionally, to prevent revisiting cells and causing infinite loops, we use a visited array to track cells that have already been explored. The next step is recursive exploration. For each direction up, down, left, and right, the ball rolls as far as possible until it either hits the boundary of the grid or an obstacle. Once it stops, we invoke the DFS function again from that stopping point, continuing the search. Backtracking plays a critical role here. After the algorithm explores all possible paths from the current position, it marks the current cell as unvisited. This ensures that the same cell can be reused for different paths during the search. Finally, we initiate the DFS process from the given starting position. The visited array, which is a 2D Boolean matrix of the same dimensions as the grid, is initialized to track visited cells. We then call DFS start row, start column to begin the search and return the result of this recursive exploration. There are several key insights to keep in mind when analyzing this algorithm. First, the recursive nature of DFS makes it an excellent choice for solving pathfinding problems, as it fully explores one path before backtracking to examine others. The use of backtracking ensures that all potential paths are considered, as it prevents the algorithm from prematurely marking cells as unavailable. Additionally, boundary handling is critical to avoid accessing invalid indices in the grid. By explicitly checking for grid boundaries and obstacles, the algorithm avoids unnecessary errors. Another important aspect is optimization through pruning. If the target position is found during recursion, further exploration can be skipped, improving efficiency. As for data structures, the grid itself is represented as a 2D array, where each cell indicates whether it is open or blocked. The visited array is another 2D Boolean matrix used to track which cells have already been explored, preventing redundant work and infinite recursion. The core operations of this algorithm include recursive calls, boundary checks, and backtracking. Each recursive call represents the decision to explore a new direction, and before moving in any direction, the algorithm ensures that the move is valid by checking for boundaries and obstacles. Backtracking ensures the algorithm resets the visited state after exploring a cell, allowing other potential paths to use that cell if necessary. Analyzing the algorithm's complexity, the time complexity is O(m*(n), where m is the number of rows and n is the number of columns in the grid. This is because, in the worst-case scenario, the algorithm explores all cells, visiting each cell once per direction. The space complexity is also O(m*(n), as the visited array requires O(m*(n) space, and, in the worst case, the recursion stack depth can reach O(m*(n) when the grid is fully open. Several edge cases must be considered to ensure the algorithm works under all scenarios. For instance, if the grid is entirely filled with obstacles, the algorithm should terminate immediately since no valid paths exist. Another edge case occurs when the target position is the same as the starting position. In this scenario, the algorithm should return true right away, as no movement is required. Lastly, the algorithm must handle disconnected regions within the grid effectively. These are areas separated by obstacles that make them inaccessible. The algorithm should ensure it correctly identifies when the target is unreachable due to such disconnections. Addressing these edge cases ensures robustness and correctness across a wide range of inputs. Here, we start by defining the findPaths function within the solution class. This function takes in the grid dimensions m and n, the maximum number of moves allowed max move, and the starting position given by start row and start column. To handle large numbers, we define mod as 10 to the power of 9 plus 7, which ensures that our results remain within the bounds of modular arithmetic. Next, we define the possible movement directions in a grid using the directions list, which includes moving up, down, left, and right. To handle overlapping subproblems efficiently, we introduce a memoization table DP, which is a dictionary that will store results for previously computed states. The core logic of the solution is implemented in a helper function, DFS, which employs recursion. It takes the current position, x, y, and the remaining moves as inputs. Within the DFS function, we first check if the current position is out of bounds. If so, it means one valid path has been found, and we return one. If there are no moves left and the position is still within bounds, no paths can lead out of the grid, so we return 0. We then check the memoization table to see if we've already computed the result for the current state. If it exists, we return the cached result to avoid redundant calculations. Moving forward, we initialize a variable paths to 0 and iterate over each possible direction. For every direction, we recursively call DFS with the updated position and one less remaining move, adding the result to paths. To prevent overflow, we take the modulo mod at every step. Finally, we store the computed result in the memoization table for the current state and return it. The findPaths function concludes by simply invoking the DFS helper function with the given starting position and the maximum number of moves allowed. This call initiates the recursive exploration of all possible paths from the starting point, considering the boundary conditions and remaining moves at each step. The result of this recursive search is returned as the total number of valid paths that lead out of the grid. By combining memoization with recursion, this implementation efficiently handles the problem's constraints, even for larger grid sizes and move limits. Here, we start by importing essential Java utilities and defining the main structure of our solution. The mod constant is set to handle large numbers and prevent overflow when calculating paths, while the directions array defines the 4 possible movements: right, down, left, and up. The findPaths method serves as the entry point of our solution. It takes the grid dimensions, maximum moves allowed, and the starting position as input parameters. We initialize a memoization table using a hashmap to store intermediate results and avoid redundant calculations. The core logic of the solution is delegated to the DFS method, which recursively explores all possible paths. Inside the DFS method, the first condition checks if the current position is out of bounds, indicating a valid path that leads out of the grid. If true, we return 1. The second condition ensures that if no moves remain, further exploration stops, and we return 0. To optimize performance, we create a unique key representing the current state based on the position and remaining moves, and check if this state has already been computed in the memoization table. If it exists, we simply return the stored result to save computation time. Now, to calculate the total number of paths, we initialize a variable paths to 0 and iterate over each possible movement direction using the directions array. For each direction, we calculate the next position by adding the direction offsets to the current coordinates. We then make a recursive call to the DFS method, reducing the remaining moves by 1 and passing the updated position. The result of each recursive call is added to the paths variable, and we use the modulo operation to ensure the value stays within the bounds of our defined mod. Once all directions have been explored, we store the computed number of paths in the memoization table with the current state as the key. This ensures that if the same state is encountered again, we can retrieve the result directly without recomputation. Finally, we return the total number of paths for the current state, completing the recursive process. Here, we are tasked with finding the number of paths that lead out of bounds on a 2x2 grid. We start at the top left corner, cell 0, 0, and are allowed a maximum of 2 moves. To solve this, we first initialize some key elements. We define a constant mod to handle large numbers by taking results modulo 10 to the power of 9 plus 7. Next, we define the possible movement directions: right, down, left, and up. These are represented as coordinate changes in the form of tuples. Finally, we set up a memoization table, represented as an empty dictionary, which will help us store results for previously computed states, ensuring we don't repeat calculations unnecessarily. The process begins with a depth-first search call, starting at cell 0, 0, with 2 moves remaining. Since this cell is within bounds and we still have moves left, we proceed to explore all 4 directions. Moving right brings us to cell 0, 1, with 1 move left, and moving down takes us to cell 1, 0, with 1 move left. Moving left or up, however, leads out of bounds immediately, so each of these returns 1 as they count as valid paths that exit the grid. For the recursive calls to cells 0, 1, and 1, 0, we follow the same exploration process, reducing the remaining moves by 1 with each step. During this recursion, certain directions lead out of bounds and are counted as valid paths, while others remain within bounds and require further exploration. To optimize this process, we employ memoization by storing results for specific states, ensuring that if we revisit the same cell with the same number of remaining moves, we can reuse the pre-computed result instead of recalculating. After completing the recursive exploration and applying memoization to avoid redundant calculations, we find that the total number of paths leading out of bounds is 6 for this example. Now, moving to a larger 3x3 grid, we start at the center, cell 1, 1, with a maximum of 4 moves allowed. The initialization remains the same as before. From the center, we explore all 4 directions recursively, decreasing the remaining moves by 1 with each step. Base cases are applied when we move out of bounds, which increments the count of valid paths, or when no moves remain, which terminates the recursion. Memoization is critical here due to the increased grid size and move limit, allowing us to store results for states like 1, 1, 3, or 0, 1, 2, and avoid unnecessary recomputation. The final result for this larger grid is a total of 80 paths leading out of bounds. In this edge case, we consider a 1 by 3 grid with a starting position at cell 0, 1, the middle of the row, and a maximum of 3 moves. The initial setup and approach remain consistent. Starting at 0, 1, we explore movements to the left and right, which stay within the grid, and up or down, which lead out of bounds immediately. Each recursive call tracks the paths for every move and direction, applying base cases when out of bounds or when no moves remain. Using memoization, we store results for recurring states, such as 0, 1, 2, to ensure efficiency. After completing the process, we calculate that the total number of paths leading out of bounds for this example is 12. To understand the time complexity of this solution, we need to analyze the number of unique states the recursive function can explore and the operations performed for each state. First, let's consider the number of states. The recursive function depends on 3 parameters: the current cell, x, y, and the remaining moves moves. Since the grid has m rows and n columns, there are m asterisk n possible positions for x, y. Additionally, remaining moves can range from 0 to max move, giving us max move plus 1 possible values. Multiplying these together, we get a total of m asterisk n asterisk, max move plus 1, unique states. Next, for each of these states, the function explores 4 possible directions: up, down, left, and right. Since this is a constant operation, the time taken per state is O(4), or simply constant time. Now, combining the number of unique states and the time per state, we can calculate the total time complexity. With m asterisk n asterisk, max move plus 1, states in each state requiring constant time, the total time complexity becomes m asterisk n asterisk max move. Shifting focus to space complexity, we consider 2 main contributors, the memoization table and the recursion stack. For the memoization table, we store results for each unique state, x, y, remaining moves. Since there are m asterisk n asterisk, max move plus 1, states in each result takes 1, space, the memoization table requires m asterisk n asterisk max move, space. Next, let's evaluate the space required by the recursion stack. The depth of the recursion stack depends on the maximum number of moves, max move, since each recursive call reduces remaining moves by 1. This means that the recursion stack can be at most max move levels deep, requiring max move, space. When we combine the space used by the memoization table and the recursion stack, the total space complexity is dominated by the larger term, which is m asterisk n asterisk max move. Furthermore, the time and space complexity remain consistent across the best, average, and worst cases because the algorithm always explores all possible states up to max move moves. This means the complexity is always m asterisk n asterisk max move. To appreciate the efficiency of this approach, let's compare it with a brute force solution. In a naive approach without memoization, the algorithm would recompute results for the same states repeatedly. For each move, there are 4 potential directions, resulting in 4 max move paths in the worst case. When considering all cells in an MXN grid, the total time complexity for the brute force approach would be m asterisk n asterisk 4 max move. This exponential growth becomes infeasible for large values of max move. In contrast, memoization avoids redundant computations by storing intermediate results. This optimization reduces the time complexity to m asterisk n asterisk max move, which is polynomial and significantly more efficient than the exponential brute force solution. Finally, let's solidify our understanding with a mathematical proof for the big O complexity. The number of unique states is bounded by m asterisk n asterisk max move. Each state is processed in constant time, 4, so the total time complexity is directly proportional to the number of states, resulting in m asterisk n asterisk max move. Similarly, the space complexity is determined by the size of the memoization table, which is proportional to the number of states, and the recursion depth, which is proportional to max move. Adding these together, the total space complexity is also m asterisk n asterisk max move. This demonstrates how memoization dramatically improves efficiency, making the algorithm scalable and practical for large inputs within the constraints of this problem. When tackling grid traversal problems, there are a few common mistakes you should watch out for. First, not accounting for edge cases can lead to problems, especially when handling scenarios like empty inputs, boundary values, or corner cases involving the smallest or largest constraints. These cases can cause runtime errors or incorrect results if overlooked, so always test your solution explicitly with edge cases. Another frequent issue is inefficient recursion without memoization. In recursive DFS, if you don't use memoization, you may end up recalculating the same sub-problems repeatedly, leading to exponential time complexity. Recognizing and caching overlapping subproblems is key to optimizing performance. Misunderstanding problem constraints is another pitfall. For example, assuming a grid has a fixed size without verifying the actual constraints can lead to unnecessary assumptions or overcomplicated logic. Finally, off-by-one errors in indexing are common when working with grids or arrays. It's easy to make mistakes in row or column indexing, especially when moving in different directions, so always double-check boundary validations for directional movements. Now, let's talk about some additional considerations. When evaluating solutions, it's important not to ignore time and space complexity trade-offs. Depending on the problem, you may need to prioritize one over the other. For example, competitive programming often requires careful evaluation of trade-offs to ensure your solution is optimal given the constraints. Recognizing patterns is another helpful skill. Many grid-based problems involve movements such as DFS or BFS, and identifying whether the problem focuses on paths, connectivity, or optimization will help you choose the right algorithm, whether it's backtracking, dynamic programming, or something else. It's also vital to break down complex problems into smaller steps. For instance, you can divide grid traversal into parts like movement validation, boundary checks, and recursive calls. Lastly, always communicate assumptions clearly. If anything about the problem constraints is unclear, like whether the ball can revisit a cell, ask for clarification. This demonstrates a structured and thoughtful approach to problem solving, which is highly valued in interviews. There are also several related problems that can help you build familiarity with similar concepts. For example, LeetCode 200, number of islands, is a classic grid traversal problem that uses DFS or BFS to explore connected regions. LeetCode 130, surrounded regions, involves connectivity and boundary checks, making it another useful example. LeetCode 79, word search, is a backtracking problem that also requires navigating a grid, and LeetCode 695, max area of island, focuses on counting connected components using DFS or BFS. When it comes to alternative approaches, it helps to know when to use recursive DFS versus iterative DFS. Recursive DFS is simpler to implement, but for large inputs, you might encounter Stack Overflow errors. Iterative DFS avoids this issue but requires more intricate implementation. If the problem involves finding the shortest path, BFS is usually preferred over DFS because it guarantees the shortest solution in unweighted graphs. Lastly, dynamic programming can be particularly effective for problems with overlapping paths. By storing results of subproblems, you can avoid redundant calculations, trading off additional space for time efficiency. Finally, let's consider greedy algorithms. In some cases, if the problem satisfies a property where making local optimal choices leads to a globally optimal solution, a greedy approach may outperform exhaustive search methods. Greedy algorithms are especially useful when the problem structure naturally aligns with this principle, allowing you to simplify the implementation while maintaining efficiency. Great job! We've reviewed problem number 576 and explored how to solve it efficiently. Remember the value of dynamic programming and memoization in optimizing recursive problems. If you enjoyed this walkthrough, make sure to like and subscribe for more coding challenges. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!